This is a three-body problem simulation in Python. These bodies are orbiting each other and this simulation is running for over 100 Earth days. But what even is the three-body problem? The three-body problem is something like this. If two bodies are in orbit, they orbit each other in a stable and predictable way. But as soon as we add a third body, the system becomes chaotic and the motion becomes very hard to predict. Sometimes the bodies even fly off. This happens because each body is pulling on the others at the same time. So the forces keeps changing and the motion turns messy. So I wondered, what if we try to simulate it and keep it stable as long as we can? My plan is to use the real physics equations to simulate the problem. So first, for a system like this, we need gravity. I am going to use the classic Newton's law of gravitation. Now this is very simple. The formula simply says that if you take any two bodies, those two bodies attract each other. The more mass they have, the more they attract each other. And the closer they are, the stronger the attraction will be. See? Simple. First, I created a gravitational constant variable. I'm not using the real value since it's too small and inconvenient for the simulation. Then I added a time step dt variable which defines how much time the simulation advances each step. I've also made a function that calculates the gravitational acceleration between two bodies. Inside this, I first calculate the distance between the two bodies, then apply the gravitational formula. But you'll notice there is only one mass. That's because the other mass cancel out when we calculate the acceleration. Also, I am using distance cubed instead of squared. Because we are working with the direction vector, so we need that extra distance to keep things correct. At last, I created three bodies with their respective properties. Pretty simple. For the orbits, first I create function which calculates center of mass of each body, create a variable that stores the total mass of the bodies. At last, I implemented the circular orbit velocity formula, which help us to keep the bodies in orbit. Let's see the bodies in action. Neat. Now let's add a third body and see what happens. As you guys see, as soon as I add a third body, the system collapses. And this is not an issue with the gravity. The physics is fine. What's actually happened is that the total energy of the system doesn't stay stable over time. Instead of staying around a fixed value, it slowly increases or decreases. And when that happens, the orbits start drifting, which eventually breaks the system. To fix this, we need a better way to update the system over time, and this is where symplectic integrator came into play. Basically, their goal is to preserve the structure of phase space, meaning energy don't grow uncontrollably. It stays bounded and keep the three bodies in a stable orbit. So let's just quickly implement this in our simulation. First, we push the velocity halfway using the current acceleration, then update the position, recalculate the acceleration from the new position, and finally finish the velocity update using that new acceleration. Running our simulation gives us this clean, stable orbit of three bodies. The simulation is correct, but visually it sucks. So let's add some trails, a star field, and a bit of glow.
A few moments later.
Wait, as I was scrolling through YouTube, I saw this shot. Someone already simulated this in 2D. But I wanted to do something different. So let's simulate this entire system in 3D. First, I call the OpenGL perspective function. This line just basically tells OpenGL how to project our 3D world into 2D screen. I've also enabled OpenGL depth test, so if one body is behind another, it won't render on top of it. In Lash, instead of placing the stars randomly, I've used Cartesian coordinates. Basically, they distribute points evenly around a sphere in full 3D space, giving us perfect position for the bodies. So let's see the final output. To be honest, this one is by far the most interesting project I have ever worked on. I hope to work more on it in future, implementing space-time curvature to simulate gravity. But that's the end of this video. Thanks for watching.